right, it's 3:30, so we'll get started. Good afternoon, everyone, and welcome to today's EOL seminar. This will be our last seminar before we break for summer. I'm Sarah Woods, and on behalf of EOL, I'm pleased to introduce Dr. Gannet Hallar, Professor of Atmospheric Sciences at the University of Utah, Director of Storm Peak Laboratory, and visiting NCAR affiliate scientist. Dr. Hallar received her bachelor's in physics from Truman State University before going on to the University of Colorado at Boulder, where she obtained her master's and doctorate in atmospheric and oceanic sciences. She has since served as the National Science Foundation Program Director of Physical and Dynamic Meteorology, as well as served many years as research professor at the Desert Research Institute in Reno, Nevada. Gannet is currently a professor in the Department of Atmospheric Sciences at the University of Utah. Beyond the university, Gannet has served the scientific community in a myriad of roles, convening several conference sessions, hosting a variety of workshops, as a guest editor for several journals, on the ARM User Executive Committee, as well as the ARM Aerosols Measurements and Science Group, which she currently chairs. She's also served as member and chair of the President's Advisory Committee on University Relations for UCAR, amongst other service and leadership positions. Dr. Hallar's extensive service has been recognized in the reception of many awards throughout her career, most recently in recognition as an outstanding teacher at the University of Utah. Amongst her long list of achievements, however, perhaps one of Gannet's most long-standing contributions to the atmospheric science community is in her dedication to fieldwork and service as director of the Storm Peak Laboratory since 2006. To hear more about Storm Peak's legacy, please join me in welcoming Dr. Hallar for her seminar titled Storm Peak Laboratory, 40-plus year history of the Mountaintop Research Facility. As a reminder for those of you joining us online, you can enter your questions in the Slido box below the presentation screen, and we'll address those at the end of the seminar.
Thank you. That was about the kindest introduction I've ever had, so thank you very much. It's really a pleasure to be here. This has been a nice experience to be visiting, and as I'm pulling together this seminar, I couldn't help but reflect on all of the ways in which EOL have been involved in a great deal of this science, and all of the ways in which ACOM have been involved in a great deal of this science. So I put little highlighted boxes on the slides to show that contribution and those collaborations. So today I'm going to be talking about Storm Peak Laboratory, which is now a National Science Foundation SIF facility, so that makes it requestable. And I want to acknowledge the co-authors here, in particular, Britt Stevens, who has done a great deal of work at the laboratory over the years. And what you're looking at here is a picture of Steamboat Springs, Colorado. And if you look up at the top of the mountain at the tallest peak, Mount Warner, that is the location of Storm Peak Laboratory. And it's located right at the Morningside chairlift, so it's actually on the ski resort. So this is an outline of the talk for today. I wanted to give you an overview of the laboratory, including a tour. Many of you have been there before, but we have completely remodeled, so I wanted you to see the facility as it's available now. And then talk a little bit about the research training at Storm Peak, and then highlight a few research projects. And the outline of this talk in all aspects is to talk about the past, how things got started, and then the present, what we're doing now on these research topics. And then finally, I'd like to mention the proposed AQUARIUS field campaign, which is why I'm visiting here this summer, is to work on the proposal of AQUARIUS and talk about that a bit, which is a C-130 request. Okay, so Storm Peak Laboratory, as I mentioned, is located in Colorado. It's located near Steamboat Springs, Colorado, within the Route National Forest. So I maintain a U.S. Forest Service permit for 1 acre of land around the Storm Peak Laboratory. And this is a beautiful symbiotic relationship because the laboratory was actually there before the ski area in that particular space. So we have a nice relationship in that we allow people to ski over the land that we have permitted, and the ski area allows us free access to the facility. So in that way, we can provide lift tickets, and we receive season passes. So bonus, right? So a little brief history of the laboratory. The laboratory was started in the late 1970s by researchers from Colorado State University. This was a grant awarded from the National Science Foundation to Lou Grant, and this was the largest award made to Colorado State University at the time, and it was really for the study of cloud seeding potential. And Lou didn't actually come to the facility or to the space until well after his retirement in 1995, so it was really a graduate student-led project in its entirety. And they began making measurements in the ski lodge. They're shown that picture in 1979. Then the researchers obtained a small trailer in 1981, and later they moved that trailer up the mountain in 1984. One thing that's shocking to me is how resilient and determined these people were to make these cloud microphysics measurements. When as mentioned, I started the job in 2006, everyone thought I was completely insane because Randy Boris and Ward Hyman, who were both have a long-standing cloud microphysics legacy, they would drift with this trailer down the mountain as the snow drifted. So the trailer would literally move with them. And they were often buried inside of this trailer, so the ski patrollers would actually have to dig them out. So all the ski patrollers couldn't imagine that anyone would take this job. So then in 1995, DRI decided to build a facility because of the long-standing problems with the trailers. And they built this small facility, which had some real challenges. And then we were very fortunate in 2012 to receive a major fund for upgrading Storm Peak Laboratory, and we remodeled the entire facility. In 2020, the lab transferred all operations from the Desert Research Institute to the University of Utah, and in 2022, all of the building, as well, all assets transferred legally to the University of Utah. So it's now a University of Utah facility, which I think provides a great deal more stability to the facility in the long term. So what is the facility? So we're located at 3,200 meters, about 690 millibars. We're in cloud about 40% of the time in the winter, and there's a 9-person bunkhouse, a full kitchen, and we have room for guest instruments as well as the facility instruments. And the facility instruments are listed here, and these include primarily aerosol measurements as well as cloud and trace gas measurements. Many of these measurements are done in collaboration with others. So for example, we work very closely with the Global Monitoring Lab at NOAA to make long-term aerosol measurements. We've worked very closely with BRIT over the years to make long-term carbon dioxide measurements. We also have worked very closely with Adriana Bailey here in EOL to make water vapor measurements. These measurements have produced approximately 150 peer-reviewed journal articles to date, and those have focused on a variety of topics, which I'll go through in this talk. So here is a brief tour of Storm Peak Lab. On the top, you can see what it looks like in the summertime, and on the bottom, you see in the wintertime. We're used for several snow hydrology field classes, and that's what you see go on there, and that's one from the University of Colorado. This is the laboratory as it's been remodeled, so this includes a wet chemistry lab. You see a chemical hood as well as a laminar flow bench. This is specifically most interesting to microbiologists, the laminar flow bench, and that's why it was put in place. It's used most frequently for that. We also have a separate instrument lab now that includes many aerosol instruments that you saw listed previously, including aerosol size distributions long-term. We have the longest record of aerosol concentration in North America, the longest record of aerosol size distributions in North America. We also measure aerosol optical properties, including scattering and absorption, as well as continuous cloud condensation nuclei at this facility. You can see there as well, we have trace gas measurements. Those include ozone, sulfur dioxide, nitrous oxides, which are done in collaboration with the state of Colorado through EPA Region 8. So we've actually been able to build a second story onto the laboratory with the upgrade in 2012. And that allows us for more room for student spaces. You can see that in the center. So we have room for students to come and work at the facility, as well as extra room for bunks. So as I mentioned, Storm Peak Laboratory is now part of the Community Instrument Facility, along with our many collaborators and peers that are listed here, which allows us to be part of the fair solicitation and a requestable facility. Okay, so under that type of request, we've recently have received 2 Track 1 awards to use Storm Peak Laboratory. This is one example of that, and that's a new University of Utah graduate field course, which I think was a very unique idea by Jim Steenberg and Sebastian Hoke, in which they used the entire mountain to teach this field course. So what they did is they actually outfitted vehicles with meteorological sensors, and then they were able to study cold pool formation using these vehicles and driving through the valley, and then also using the lab at the same time. But not all of our field classes are funded via NSF Track 1. Many of them are actually funded through individuals or through the universities themselves. Sometimes they have field courses associated, field costs associated with these, like field fees. That was one big advantage of adding this NSF solicitation, in that no longer would students have to pay fees to use the lab. But there are many classes that use the lab on an annual basis, including Colorado State University, Hendrix College, and Texas A&M every year. As I mentioned previously, you saw a picture of the University of Colorado. Noah Moloch integrates a snow hydrology course with Katja Friedlich here at the University of Colorado in an atmospheric science field course, so that each major learns a little bit more about the other. So approximately 100 students annually use the lab for field courses, and it's allowed for about 40 graduate students to use data for their master's or PhD. So one thing I also wanted to mention that we do quite a bit extensively at Storm Peak Laboratories, we've had a long history of having field programs for underrepresented students. And we really appreciate the support from NCAR to provide these opportunities. And in particular, we had a program called GRASP, which was funded by Opportunities for Enhancing Diversity at NSF for about 7 years. And that program had students go to Storm Peak and then come here to RAF and take tours. And you can see some of the pictures there for those tours. We now have a somewhat similar but slightly different program, which is called REALM, which has been funded for 4 years, and that's research in alpine meteorology, which has about 8 students this summer, and they stay at the University of Utah for 10 weeks. And this also involves 1 week of training at Storm Peak Laboratory. And one thing I'd just like to point out is that if the potential is available in the future, we'd love to have the students also come to EOL and have that experience again. So now that kind of covers the outreach and the tour, and now we'll go on to the research that we do there, okay? And I like to start with this figure because this, in a way, drives everything that we do, both in our research group as well as in at Storm Peak Laboratory. And of course, this figure will be very familiar to many of you, but this was the last IPCC report, and I had a graphic artist try to make it a little less of a confusogram for the general public. And this is showing those major climate emission drivers. And what you see is, of course, at the top, we start with carbon dioxide, and we've, through our collaboration with Brit, have been measuring carbon dioxide for quite a while at Storm Peak. Then we move on to methane, which we were very excited to have a collaboration with NOAA that just started in 2022. So we added a Picaro instrument for the measurement of methane at Storm Peak Laboratory. And then we look at aerosols and their precursors. And in particular, it's important, of course, to know not only what the aerosols are, but what they are made of. And so we do a lot of work on aerosol chemistry at Storm Peak, and then the cloud adjustment due to aerosols. And as I mentioned, we have cloud microphysics measurements at Storm Peak that we are doing on a large wind vane that was actually built here, the wind vane in collaboration with the machine shop here. And through that, I'm going to go through that one step at a time using that framework. So we'll start with carbon dioxide, methane, aerosols, and then clouds. So here's a figure that Britt made showing the record of carbon dioxide starting back in 2005, even before I was at the lab, and ending in 2018. Of course, as I mentioned, we've added some instruments through NOAA, AQUARIUS, so we now will have that measurement continuing again. And an undergraduate student in my group is working on syncing those two data sets. And this data set, I think, needs to be highlighted because it's been used many, many times and has a great deal of power. And this is one example of a paper that was a collaboration between Britt and several colleagues of mine at the University of Utah that really showed these observations from Storm Peak Laboratory could be used to show a clear signal of carbon dioxide uptake in western forests. And they could also show where there's limitations in potential of models. So specifically, as it says here, the nighttime data is the least influenced by the local process. However, these coarse resolution models show a strong local influence at night, suggesting the need for a higher resolution modeling. And the other thing I just wanted to point out is that this data has been downloaded over 1,000 times. So showing the power of this data set and how many people are using it. Continuing on the bent of atmospheric chemistry, Storm Peak Laboratory has a long history and many papers focusing on the transition of mercury through the atmosphere. And in particular, this is a figure done by Seth Lyman here at the bottom that illustrates the importance of atmospheric mercury. So for those who aren't familiar with atmospheric mercury, you have gaseous elemental mercury, which is actually pretty innate. It doesn't bioaccumulate, it is not harmful. But if that mercury oxidizes, then it becomes harmful both to ecosystems as well as humans. And understanding the relationship between these two has been a big focus at Storm Peak. So Daniel Obrist started making measurements back in 2006. We started making these measurements together. And what we found was that you could see strong increases in mercury that were related to air masses coming from East Asia. So we saw these increases in mercury during those time frames. Then he had his postdoc, Xavier Fain, come and look at, well, we saw the elemental mercury, which again is not harmful to ecosystems, but now what about the reactive mercury? So we added some additional instruments and looked at reactive mercury. And what you see here is that the reactive mercury did not follow the same pattern, leading to more questions and answers, but we saw a lot of relationships for the first time regarding relative humidity in the atmosphere and its relationship to mercury. So that led to a large field campaign that we are just concluding. It finishes at the end of 2023, in which a group from Utah State University, Seth Lyman, Lynn Gratz from Colorado College, and Reiner here from the University of Colorado have put together a new instrument which involves the measurement of gaseous elemental mercury as well as reactive mercury, which are commercially available instruments, but they've added a new measurement techniques in which they can actually calibrate those instruments. And that was deployed for the last 2 years at Storm Peak. Simultaneously, what we're interested in is where the oxidants are allowing for that transformation between the elemental mercury to the reactive mercury, and that's being measured by Reiner's Max DOAS at Storm Peak. And that's been up there for approximately 2 years as well. Another aspect of atmospheric chemistry that we've had a lot of focus on at Storm Peak is the implications of infestation on volatile organic carbons in the atmosphere. And this project really started with an ACOM collaboration. I'd like to thank Alex Gunter at the time. He really gave me a few samples and was able to do a few samples for us that ended up spawning years and years of work. What we were interested in is, for those of you who remember the incredible mountain pine bark infestation in the 2008, and what we saw was during this infestation, we were seeing changes in our aerosol concentration. We saw increases in our aerosol concentration. And what we did is we went out and took personal samples on the trees themselves, and we took control samples of healthy trees versus non-healthy trees. And we worked with Kara Huff-Hartz at the University of Illinois, and were able to identify what types of volatile organic carbons were coming from the infested trees. And we actually were able to show that beta-philandrin is actually a signature of these infestations. So we were able to show the amount of volatile organic carbon that came off of each tree in comparison to a healthy tree. And then Colette Held was able to run a model to show how would that change the secondary organic aerosol concentration in the atmosphere with those additional volatile organic carbons. And what she showed was that there was a very significant increase, up to 40% in some places, but a significant increase due to both, if you combine the mortality of the tree and the attack itself. So that led us to continue to think about, okay, so how much of the aerosol itself is organic, and are these aerosols actually able to form cloud condensation nuclei? That spawned another NSF field campaign and another study that lasted many years. You can see we started making measurements in 2010, and papers are still coming out in 2019. But what we did is we took many different filter samples and sent them to different labs across the country. This is Lynn Mazzoli from Michigan Tech. We also have people from Denmark here. And what we did is we analyzed the chemical composition, specifically the organic concentration of the water-soluble organics on those filters, and did intercomparison between different techniques, and then tried to calculate out what was the hygroscopic parameter, or essentially how much water can those aerosols uptake, and then how does that impact, or how that tells us about, their ability to make cloud condensation nuclei. This was one of the most comprehensive studies of water-soluble organic to date. Okay, another thing that I would say has really been sparked initially by collaborations with AECOM is we started making measurements of aerosol size distribution. And what we found at the time was quite surprising. So this is an aerosol size distribution. On the left axis here, you have sizes. We're starting on the top at 3 nanometers, and on the bottom we start at 8 nanometers. And we go up to about 300 nanometers here and about 70 nanometers there. On the x-axis, you see time, and the colors coming out at you are concentration. And what you're seeing here is this burst of particles which continue to grow and grow and grow. And they grow up to about between, well, in this scenario, they grow up to 40 nanometers. In this scenario, closer to 70 nanometers. So what you're looking at here is new particle formation events. So gas to particle conversion allowed for the nucleation, and then those particles start to grow. And that growth is seen throughout the entire day, starting with sunrise and going all the way to the evening. And what we found is when we started analyzing decades of data, we found that this happens about 56% of days, which is incredibly high of those 306 days analyzed. And we also found that that was associated with increases in ultraviolet light, pointing us towards photochemistry. So then we looked at, well, what is happening those days? It's allowing for those particles to form that might not be happening other days besides the light, besides the increase in ultraviolet light. And what we saw is that there's a certain wind direction associated with days with new particle formation. And that those days with new particle formation events are coming almost directly out of the west. And that wind direction is also associated with sulfur dioxide. So if you go directly west of Storm Peak Lab, what do you see? You see the Hayden Power Plant, the Craig Power Plant, and the Vernal Power Plant that follow Highway 40 straight to Storm Peak Laboratory. So this has been a pretty interesting study showing that what we see is the formation of sulfuric acid, which is acting as a seed to help nucleate these particles. This is leading us to a lot of questions, and I would say this and a couple other studies that have been done in Europe are leading people to questions. What happens when these power plants shut down, as is scheduled in the next decade? What will happen to the aerosol load at Storm Peak Laboratory? And is there enough background SO2 to allow for this nucleation to continue happening, background sulfuric acid? Taking that a step further, we, as I mentioned, make continuous measurements of cloud condensation nuclei, which is essentially a measurement that tells you whether or not an aerosol particle can become a cloud at a very specific supersaturation. So we make continuous measurements of cloud condensation nuclei, and we were able to take 15 years of that data. Most recently, this is a graduate student who just finished his master's in my group, Noah Hirschhorn, and what he was able to show is that the days with new particle formation have a significant enhancement in cloud condensation nuclei in comparison to the days without, especially in the winter time where you see about a 36% enhancement, in the springtime with a 54% enhancement. So not only is that sulfuric acid allowing for these, is providing a seed to allow for the nucleation, and combined with biogenic volatile organics that are there, but it's also allowing the particles to grow large enough that they actually can uptake water and thus have a more significant impact on the climate. So I wanted to say that, of course, these are just some examples of our research group work using aerosol data from Storm Peak, but there are many others that have been using aerosol data from Storm Peak on this same type of vein, specifically in looking at nucleation parameterizations and models and how to improve that, and also looking at trend analysis, especially as it pertains to wildfire smoke, dust events, et cetera. And this is one example of trends in aerosol scattering in which Martine Collin, she saw differences at Storm Peak than in other places, which led to several follow-on papers about wildfire impacts on overall aerosol in the Western United States. Okay, so that finishes the aerosol side. So we're now going to move to the cloud side. And I would be remiss in not talking about ISPA if you talk about Storm Peak Laboratory, because ISPA is really what started Storm Peak Laboratory, and that is the inhibition of snowfall by pollution aerosol. And that was an idea from Randy Boris, who wrote this paper and subsequent many following papers, and you'll see some co-authors here in the audience for sure who contributed extensively to this work. What he was able to show is, I wanted to introduce the idea of cloud condensation nuclei first before you talk about ISPA. But with cloud condensation nuclei, what you can do is if you have more particles, so you have dirty air in the case above here, if you have dirty air and the same amount of water, you essentially spread that water amongst more particles, creating smaller cloud droplets, okay? So here you see these smaller cloud droplets. We're talking about the TUI effect. In the bottom here, the clean, you have the larger cloud droplets. Okay, now those cloud droplets are interacting with snowflakes. In the scenario at the top, the dirty small drops pass around the snowflake, aerodynamically missing the snowflake, allowing for this artificially, I'll just say, this is a picture from Ken Liebrecht. This isn't a picture we took at Storm Peak Lab, but an artificial image here, but a picture of a very clean, pristine, not rhymed snowflake. In the scenario on the bottom, you have a clean scenario where you have very low aerosol concentration, thus you have these bigger cloud droplets that impact that snowflake directly, and you end up with more rhyming, okay? That's the theory of ISPA. This theory was tested with a instrument built by Randy that was pretty simple but kind of ingenious, which simply took videos of snow for long, long periods of time. And then at the same time, he collected snow and cloud water and measured that for sulfate. And over the course of many years, with many help from EOL, he was able to show that when you had unrhymed cases, you had the sulfate concentration for unrhymed cases was about 9 times higher than found in rhymed cases. This led to many follow-on studies and many people, and I just want to say thank you to the entire atmospheric profiling team, especially Bill Brown, for all of the years of work doing this. But why do we care, you know, if a snowflake is rhymed or unrhymed, and if this sulfate aerosol is making that difference? And I will say we cannot repeat these because the power plant's cleaned up significantly with scrubbers, so we don't have anywhere near the sulfate concentration we used to. But the reason you care has been shown by Bill Cotton's group several times, including this paper, in that the idea is when you think about the mountaintop, you have spillover of snow. And here in the western United States, we of course need more water on the west side and we need less water on the east side. And if you have these very pristine snowflakes, going back one slide, then these can fall more quickly onto the wrong side, is the best way that I think about it. And thus, this became incredibly important when you started thinking about water and water resources in the western United States, that essentially pollution could allow for more pristine snowflakes, which would have a stronger spillover effect onto the east side of the mountain. So on that note, when you're thinking about clouds, so far we've talked about cloud condensation nuclei, and now I'm going to switch over to give you a broad overview of Storm Peak Lab and talk about ice nuclei. And I would say, going back again, starting with the history, some of the very seminal work on ice nuclei was shown by in the 2000s from Storm Peak, and Paul DeMott's PNAS paper, which was from a campaign called Inspect. And that paper was really the first one to say that metals and mineral dust appeared to dominate the IN composition. That campaign then followed with Inspect 2, which was held at Storm Peak Laboratory and involved many more instruments to help verify this. And I would say that work has continued in 2015, in which we had a massive upgrade to the lab to get enough power to be able to do this. So we added 5 ice nucleation chambers simultaneously, which required more power and air conditioning. But in order to compare different measurement techniques for cloud condensation nuclei, some of those measurement techniques include a CFDC, which is the common technique that's been used here by DeMott, and a new PINE instrument, which I'll talk about with the next slide. So most recently, we had an NSF project which was led by Dan Sitso at MIT, and then during the project, he moved to Purdue. And this is for a new inlet called Spider. And this inlet actually is created in that it can separate droplets, ice, and vapor in mixed phase clouds at the surface. And the way it does that is it has a PVCI at the top, and then it has ice walls at the bottom, which allow for the Bergeron process to pull the ice off. This allows you to have the drop residuals and the ice residuals, and then you can attach an ice nuclei chamber to the channels. And I want to acknowledge Adriana Bailey, who I know is online, because what really allowed us to have confidence in this technique is that Adriana was able to set up water vapor isotope instruments to the different channels and determine that we were measuring what we thought we were measuring. And this is just an illustration of that system. Here is the Spider inlet, and then here is a PINE ice nucleation chamber. Here's a single particle mass spec to understand the chemistry of the ice nucleation chamber from last year. And that brings me to kind of our most recent work, which is looking at ice nuclei. So what we have been doing most recently is being used for commercial companies. So Handix Scientific here in the Front Range, they did the first long-term measurement of ice nuclei in the United States. They started in October of 2020 and ended in January of 2020, which, as you can imagine, COVID was very challenging. And then PINE, which is a new instrument that is a adiabatic chamber for the measurement of ice nuclei, portable ice nuclei environment. They set up in October 2021 and just ended in 2023. So what we're finding is pretty exciting. Not to be no surprise there, but we're seeing extremely high number of ice nuclei during dust events. Okay, then a little bit more about the history of ice nuclei at Storm Peak Laboratory. Really, some of the first studies showing that biological aerosols act as ice nuclei were done in the 1990s by Gary Franck, who we've named the chemistry lab after. He really showed this cloud activation characteristics very early on of cells. And I would like to thank ACOM for continuing this work. Christine Wiedemeyer and others led a campaign called Storm Peak Aerosol and Cloud Characterization Study that was quite insightful, in which they involved Bob Bowers from the University of Colorado to do collection and pyrosequencing to really understand what type of aerosols, what type of biological material was available at Storm Peak. And then he did drop freeze assays to see whether or not they made ice. At the same time, I ran an online UV APS, which is an aerodynamic particle sizer with a UV channel for fluorescence that can provide information about ice nuclei, about biological material. And we collected filters for many other people. This resulted in some interesting papers, and overall I'd say the major results is that 40% of the organic carbon is biological, though that's a highly, highly uncertain, and really unique seasonal diversity in these bacterial communities. That 2008 campaign has really sparked a lot of work at Storm Peak on reinvigorated, I would say, biological aerosol work at Storm Peak, and I'd say many other places as well. And these are just some of the most recent results that I really wanted to show that involve samples that we collected at Storm Peak using the new clean room laminar flow bench, in which bacteria and fungi was very high concentrations, and have also seemed to have a very different characterization from other places. So you can see Storm Peak Lab here appeared to be most similar to samples that were taken during a hurricane rather than in the snow or coastal environments. So it's been quite exciting. Okay, now continuing on the theme of clouds, but moving on to remote sensing, I wanted to talk about some of the remote sensing work that's been done at Storm Peak. And I wanted to start with the Storm Vex Field Campaign, which was funded by the Department of Energy, our radiation measurements. And what we did here was, this was led by Jay Mace and Matt Shoup, shown in that picture right there. And here we were able to work collaboratively with the ski area and put a W-band scanning radar at the gondola. And they have allowed us to do this anytime we want, which is really, really nice. And then we were able to put measurements at the valley and then add a shipping container at Christie Peak at the top of the chair for the measurement of aerosols. And then we have Storm Peak Laboratory. And the real intent of this campaign was to try to validate the W-band radar that was at the gondola with the cloud microphysics measurements at Storm Peak Laboratory. And so that, you'll see balloons being launched here. We have the W-band radar here, total sky imager here. There were many, many measurements. And I obviously can't talk about, that would be all I talk about today, but it did result in quite a few different studies of ice crystal habit from a scanning W-band radar. I'd say this is the most impactful paper if I had to pick one at the top here. Enhanced radar backscatter due to ice crystals. It's really brought a lot of insight into the W-band. And with that in mind, Claire Peterson is now working at the University of Michigan in collaboration with their new hire, Adriana, to do a campaign called Snow Climb, which will have we hope will have, it's being proposed, I should say, we hope we'll have the sea-pole radar, which we've sited outside of Storm Peak Laboratory. We've found a spot for it. And the Casper radar, which would be at the gondola building, in order to do this study again using cloud microphysics measurements at Storm Peak Laboratory again. And here I see real potential, as I mentioned to several of you, for collaboration with EOL, specifically with pertaining to the cloud microphysics measurements. So we have a SIP and a PIP, and we're planning to add a Pallas cloud droplet probe to replace our FSSP, but we're really missing things like the holodeck and other instruments that would be extremely helpful here. Okay, I hope I'm not too long on time. Okay, so with the few minutes I have left, I wanted to talk quickly about why I'm here this summer. I'm here until August 15th, and I would be so happy to speak with all of you, to be honest. I'd really appreciate getting to know you. For those of you I don't know. And I'm here on behalf of the AQUARIUS science team, which is shown in this long list right here, of people who were all co-authors on a white paper that we wrote together that has been published in BAMS. And that's to plan an airborne field campaign using the C-130. We'd like to see this campaign happen in winter 25-26. And the idea is really to couple air quality and boundary layer meteorology in this field campaign. And this paper gives the design and rationale for that study. We have collaborators at NOAA, and we have some potential for other airplanes to be involved at this point. And we're also hoping to involve the C-130. So AQUARIUS stands for Air Quality Research in the Western U.S. And again, this is proposed for the winter of 25 and 26. And it's really to investigate particulate matter in the mountain basins of the Western United States. Through a workshop that we hosted in September of 2019 and many subsequent team meetings, we have focused in on two primary locations, the three populated valleys within Utah, including Salt Lake, Utah Valley, and Cache Valley. Cache Valley being primarily agriculture, more agricultural focused, and then the San Joaquin Valley in California. This workshop did include 120 attendees representing 50 institutions in 5 countries. But the reason that we're focusing on these locations is because in Utah, you have a dominant ammonium nitrate aerosol. About 75% of the aerosol by mass is ammonium nitrate, where in San Joaquin Valley, that is primarily organic aerosol. So both are formed through secondary formation. They're both secondary aerosols, but they have very, very different chemistry. So the idea is to compare and contrast the implications at the two different valleys. And one thing that has been done previously in Utah is a campaign in 2017, which was called the Utah Winter Fine Particulate Study. And from that study, we really understand much more deeply the importance of understanding the boundary layer meteorology in these mountain basins, as well as the chemistry. There were certain things that were just missing. And greenhouse gases will help us get there as well. So this is the organizing committee. I definitely have to acknowledge all the teammates on this organizing committee, and we have put together this plan thus far. This is a figure from the BAMS paper where you can really see the goals of the study itself, understanding the emissions as well as how the radiative impacts, how do these persistent cold air pools form, the chemical cycling that happens, the aerosol cloud interactions, et cetera. You're looking here at ideas for stationing planes. So we're looking at having a twin otter from NOAA both at both locations as well as the P3. And the question is, will the P3 or the C-130 where we would base? So again, this is really looking at these short-lived pollutants, especially looking at NO and NOI, particulate matter formation, and greenhouse gas and inventory. Just because I wanted to end on a funny note, what's in a name? So this was done by one of my former students who's not at Purdue. So he came up with the name AQUARIUS, which if you saw how that acronym was made, it was quite tricky. You had to do an AQ, then a U, it was quite hard. But he did that because Aquarius is a winter constellation in the Northern Hemisphere. Aquarius sign is during when we'd like to be flying. The aqua in its name, it's the sign of the zodiac for air, which is good. And it's Latin for water carrier, which is a mystical healer who bestows water or life upon the land. It's considered the most humanitarian sign, which shows that he cares about air quality. So this all makes sense. And then also the symbol looks like a mountain wave. So you got to give it up to, his name's Chris, for being so creative to come up with all of this. So, and I'd just like to say thank you very much for your time, most of all, and your attention. And then I want to acknowledge our current research team, as well as my kids at the top there. Oh, sorry, that's a bad picture of Megan. I need a better picture of Megan, but that's the current research team, some of which are going to come out this summer and join me, so I'm really excited to introduce you to them. And of course, we need to acknowledge all of our funders. So thank you very much for your time.
Thanks, Gannet, for that really interesting talk.
You're so welcome.
So much history there. I don't see any questions online yet. Do we have questions from those in the room?
So sorry.
Nice seminar. I have a question on the rhymed, unrhymed ice particles association with cloud droplets, smaller and big.
Yeah.
Could you comment on what the size difference between small and big drops and concentrations?
Absolutely, yeah. So I'm going to just go back to that slide so everybody sees what I'm talking about. But so we were just talking about this, Sarah and I, right before the seminar, so your timing's perfect. So what typically the size distribution that we've seen from the FSSP over the years has a mode of about, has a mode of about 10 microns. So the droplet size distribution in a clean condition. And that's since I've been there in 2006. What Randy was able to show in these dirty conditions is it going down to about 5 microns, so a smaller drop in the size. Yeah.
The concentration, anything difference between them? The lot more concentration in the small particles compared to larger particles?
Yes, one of the figures in actually this paper shows a difference in the concentration, but I can't recall what it is off the top of my head.
Thank you.
Yeah, of course.
Yeah, great question. We do have one online from Carl Drews in ACOM. How and how often do you clear the rime ice off the SPL instruments?
Well, it depends on the instrument, so I'll say that. So that's a good question. So we've worked extensively with DMT to redo all of the optical heating for all of our cloud probes. So they are redesigned for surface measurements, which has been quite interesting process. We also had a mechanical engineer named Rick Purcell actually worked here for a little bit with your machine shop to design our inlet to have heating. So what we try really hard is to have things that are self-de-icing as much as possible. That being said, that doesn't always happen. There was a study from NOAA Global Monitoring Lab in which they set out a bunch of radiometers for a winter with cameras to look to see whether or not they were rhyming over and to try to determine which was the best radiometers to use for the ITAC due to rhyming. So that's a long answer, but honestly, we have a tech that goes up twice a week too.
Nice. Any other questions?
Hi, Gannet.
Hi.
An early version of the AQUARIUS proposal that we saw had a surface component.
Yes.
But you've just talked about aircraft. Can you talk anything about surface measurements?
Yes. Okay, so that's a very good question. So I will say we have divided task. So I am here this summer to work on the aircraft portion, and Eric Crosman is leading the surface-based portion of the AQUARIUS. And he is definitely the expert in that regime, so I don't want to speak too much about that. But we, of course, are requesting the ISFS and the ISS.
Good.
Yeah, I'm sorry.
And just to follow up, is that in both San Joaquin and Utah that you'd want surface measurements?
So we didn't think we could do both. I think Eric should talk to you about that. We were assuming that we would only have those in Salt Lake.
We always say, request what you want, not what you think you can get.
That's awesome. Thank you. Thank you.
Very good advice. We have another question online from Adam. How detailed are the chemical analyses of the samples? More specifically, can you differentiate between non-natural anthropogenic organics?
Yes, okay, that's a very good question, whoever asked that question. So it depends upon the project, I'll say more carefully. So we do not have a continuous aerosol mass spectrometer, or ACSM. So what we do most frequently is we collect filter samples for different laboratories to do off-site analysis. So that really would vary, particularly on the lab that it goes to. So for example, I showed a picture of Lynn Mazzoli. She's getting it down to she literally had one sample from Storm Peak. She could identify something like, I can't remember, it was like 15,000 different organics on a single sample, So that's the most extreme case. In other cases, we send things to the Desert Research Institute to do inorganics at a more simple level. I don't know if I answered that question well, but if you have a follow-up question, Adam, feel free to type it in. So not continuously would be the answer, but we do for for specific studies, we'll do samples to answer those questions.
Great. Any other questions from the room?
Thank you all for coming very much.
All right, I don't see any more online, so I have a question for you.
Yeah, totally.
With so many years of running so many projects at Storm Peak, do you have a favorite field project?
Ooh, IFRAX was pretty fun. Bill was there. That was a fun one. That's a good question. StormVax was not it. That was exhausting. It was great, but it was really hard, actually. Just to say why. So StormVax, we had staffed the whole thing to be in cloud 40% of the time, which is our average if you look at 20 years of data. And we were in cloud 68% of the time, which just was exhausting because we had to be, we just had to work that. It was really hard, actually. Yeah, exactly. To answer, yeah. So he wrote back. So samples are extracted from filters at different labs. That's exactly right. Yeah. IFRAX was fun. Yeah, I don't know what's my favorite, but IFRAX was really fun. Bill, you've been there for a lot of them. What's your favorite? 5 times, 5 of them?
I like this one.
The new one. That's awesome. ISPA. Yeah, ISPA. ISPA 2 or ISPA 1? Yeah, that's fun.
Yeah, that looks super exciting, as does AQUARIUS. Very fun. Well, if there are no other questions from the room, and I don't see any other online, again, Gannet's here till mid-August if you'd like to meet with her. And Gannet, thank you for a wonderful presentation.
Of course.